Okay, welcome back. Before we get into the second part of the 5.2 topics, just a reminder that if you've been watching these videos or you're just starting, again, try to get into some good routine. My advice in my original email from Monday was that to take one day to watch these videos, study the sections, reread some things, and start the problem set. The next day, continue working through the problem set, making notes of anything you might struggle with. And again, please try to budget the time. Either it's the normal first period or seventh period of the day or any other time you have of the day. But if you can get 45 to 50 minutes to an hour each of those days during the week, you should be in good shape, at least to be ready to move on to a next course and be comfortable with this topic. Okay, so second part of section 5.2. Again, we're trying to build a geometric understanding of what integration is all about. And here, we are going to consider the area under a curve. So if I draw some random function, and let's just say we want to take a look at this area from maybe A to B. There's obviously an area under this curve, but it's not a regular type shape. What we are going to do is start to build a foundation for how can we find that. Well, if I would tell you to just approximate the area, one option would be to maybe just think of a rectangle that looks like it's about the same. For example, we might have a rectangle that's maybe about this big, and if I could calculate that area based on this function, and then I knew what these values were for the function, I could get an approximation for the area. Well, another option is to break it up into smaller rectangles and smaller rectangles. So here's one idea. What if I would take this interval from A to B, and I'm just going to chop it up into 4, what we could call slivers. And at each of those points, I'm going to build a rectangle that is either totally beneath the curve or totally above the curve. Here's what it might look like. On this interval, the rectangle may look like this. Here, we go up to the curve and straight over, so we make a new rectangle. And we go up to the curve, over, we make a new rectangle. Up to the curve, over, make a new rectangle. If I add all of these rectangles together in terms of their area, I basically have an approximation for the area under the curve. Now, because I have made all of these rectangles what we call inscribed underneath the curve, I know that this sum is definitely lower than the real area. So we can call this the lower sum. Now I could do a similar thing. I could come up on each little section with a rectangle that is totally above the curve. For example, on this section, if it was totally above the curve, it would have to be this blue rectangle. And then from here, it would be this blue rectangle. Then I'm going to continue to think of rectangles that are what we would call circumscribed. In other words, they are outside the curve. So if I add the sum of the areas of these blue rectangles, I get the upper sum. So in order to find the area under the curve, what I'm starting with is just to divide this into a couple, 3, 4, 5, 6, 7 kind of vertical strips or representative rectangles and adding the areas of those rectangles. So as long as you can find the area of rectangles, you should be able to perform these problems. Now, if I want to get a better estimate, we have a lot of things we can do. One is to have more rectangles. I could chop this into 16 or 32 or 50 or maybe 1,000,000 different little sections. Well, that would be silly to calculate, but it would keep giving me better and better approximations. The other option is to maybe take the lower sum and upper sum and average them. So you know what? I think the area is about the average between these two. Now, it's not going to be exact, but it will be approximation. We do have one other option, and that is to use what's known as the midpoint sum. The midpoint sum uses the midpoint of each interval to establish how high the rectangle is. For example, I'm going to use the midpoint of every single one of these intervals, and that is going to help establish how tall the rectangle is. Now the rectangle is still going to be built on the original interval. Now the midpoint sum is not the average of the lower sum and upper sum necessarily, so we can't assume that. But the midpoint sum is still just adding a bunch of rectangles together. So that's kind of the theory behind trying to find the area underneath a curve. Let's take a look at a specific example. Let's say my function is f of x equals x cubed. And I just want it to be on the interval from, let's just say 1 to 2. So if I sketch it, let me do something a little bit different. I'm just going to go from 0 to 1. So at 1, the function is 1. We know x cubed looks like this on that interval. So basically, I'm going to try to approximate the area of that irregular shape. Now, I'm going to do it by finding all three of these, upper sum, lower sum, and midpoint sum. Also, I need to know how many intervals to divide it into. So I'm going to say let n equal 4. Okay, so let's find the upper sum first. I first divide this into 4 parts. When I do that, I know that's 1/4, that's 1/2, and that's going to be 3/4. Okay, so the upper sum would basically be the sum of the areas of all of these rectangles. Upper means above. So if I can find the areas of those rectangles, I'm good. So the upper sum. Now the base of every single one of these rectangles is 1/4. So it's going to be basically base times height, base times height, base times height, base times height. The height is what changes. The height of this rectangle here is going to be 1/4 cubed because that's the function. The height of this rectangle is 1/2 cubed. The area or the height of this one is 3/4 cubed. The area of this one is going to be 1 cubed. Now I'm not going to do this calculation here. You can go ahead and check that out. But that would be considered an upper sum. Lower sum. Same idea, but I'm going to be using these rectangles. Now this first rectangle basically has no height, so there isn't even a rectangle. But I can still include that. It's going to be 1/4. It's going to be that basically 0 cubed plus 1/4 cubed plus 1/2 cubed plus 3/4 cubed. Now it's going to be important to write out this initial step for upper sums and lower sums. Then after that, you may use a calculator, at least in this course. Let's look at the midpoint sum. The midpoint sum still uses each of these bases. So the base of every rectangle is going to be 1/4. Now, the rectangle height is going to be established by the midpoints of every single one of these. The midpoint of this one is 1/8. The midpoint of this one is 3/8. The midpoint of that is 5/8. Midpoint of this is 7/8. So we have this height is going to be 1/8 cubed. This height will be 3/8 cubed plus 5/8 cubed plus 7/8 cubed. So, do all these calculations, compare them, and you can get a feel for, yes, the midpoint sum should be between these. This is the lowest it possibly can be. This is the highest it possibly can be. This is somewhere in the middle. This is probably your best one-step estimate, of course, if you're asked to do that. Realize some of the differences is that I'm not always going to be going from 0 to 1. It could go from 1 to 7. This n could change. I could want 8 rectangles. It's just more calculation. Hopefully you see how this topic could somehow connect to our previous topic in this section, and that is summation notation. I can possibly write this as one nice big summation notation as these rectangles, the number gets larger and larger. Not something we typically do, but it can be done. So, the problem set is going to be about finding upper sums, lower sums, and midpoint sums. I will state this. It talks about using a midpoint rule. Don't worry about the formality of that rule. Just go ahead and do it the way I did it here. Also, it'll talk about finding the exact area using the limit process. I think problem number 49 asks you to do that. Skip it. We are not going to be responsible for finding the exact area. Now, if you think about what that would entail, is we would have to have an infinite number of rectangles. And if we want to add an infinite number of things together, we would have to use limits. And that's how this whole semester started. So there would be a lot of other neat connections we could make if we were meeting each day, but it's not something at this level that we really need to be responsible for. So, section 5.2, we have sigma notation, which represents sums. We have this area under curves, which is just a bunch of rectangles added together. There could be times where the rectangles are getting smaller. You could have a function that goes up and then back down, like sine or cosine. So again, just understand, lower sum, all the rectangles have to be totally beneath the function. Upper sum, the rectangles are above. Midpoint sum, somewhere in between. Good luck with the problem set. Let me know if you have any questions, and look forward to Friday to have one more of these video lessons. Have a good day.